In this supplementary video, I'd like to talk a bit about the relation between Dedekind cuts and our everyday representation of real numbers as infinite decimals. And furthermore, I'd like to talk about binary expansions of real numbers, since we'll be dealing with those when we talk about the diagonalization argument. Whenever we do a computation involving a real number, we most certainly do not think of these real numbers as Dedekind cuts, or even as equivalence classes of Cauchy sequences. What we do is we think of these as infinite decimals. That is, we don't think of the square root of 2 as a subset of the rational numbers with this predicate. What we do is we think of the square root of 2 as this infinite decimal expansion, which we would always truncate at some location depending upon what level of accuracy we need for our computation. So the question I'd like to talk about in this video is how we might think of converting between these two representations, between this very theoretical representation of the square root of 2 and the infinite decimal, and at the same time very practical representation of the square root of 2. If you've done any applied mathematics, you're probably very used to seeing these decimal representations, but sometimes we forget about what this notation means. So I'd like to spend a moment reflecting upon what we mean by something like 1.4142, which is a truncation of the square root of 2. So what do we mean by this notation? What we mean is that the representation 1.4142 means 1 plus 4 over 10 plus 1 over 100 plus 4 over 1000 plus 2 over 10,000. And here we're working in decimal, meaning that we're working with powers of 10. So the digit in this location means how many copies of 10 to the 0 power do we take? And this is why we call it the ones place. The digit in this location is the tenths place, or 10 to the minus 1 place. So this is how many copies of 1 over 10 we take. And this is the 10 to the negative 2 place, the 10 to the negative 3 place, and 10 to the negative 4 place, and so on. And the digit tells us how many copies of that we're taking. So this is our everyday representation of this number in base 10, or decimal. So the question I'd like to ask now is, why is it that this first digit in the square root of 2 is 1 and not 0 or 2? The reason being that 1 squared is less than 2, but if we go one more digit up to 2, 2 squared is going to be greater than 2. Because remember that this number is supposed to be the number such that when it's squared is going to be equal to 2. So it has to be 1, because if we go up one more place, it would start to exceed 2 when we square it. And correspondingly, we ask a similar question of the second digit. Why is it 4 and not 5? The reason being, if it's 4, we form the fraction of 14 over 10, because 1.4 means 1 plus 4 tenths, which is 14 over 10. We square that and we get 196 over 100, which is just slightly less than 2. But if we go one more up to 15 over 10, we square that, we get 225 over 100, which is greater than 2. And furthermore, we want the second digit to be 4 and not 3, because 13 over 10 would also, so 1 squared would also be less than 2, because we want the largest digit, such that we can get a rational number such that when it's squared is still less than 2. So this is the general pattern that we find here. So when we move on to the third digit, it has to be 1, because 141 over 100, so 1 squared, produces a rational number which is slightly less than 2. But if we go one more place up to 142 over 100, square it, we get a rational number which exceeds 2. So this is sort of why the digits are the way they are in the square root of 2. And also assuming that we're working in base 10. This is why working in this base sort of determines which digits are going to be here. So the general observation that we're going to make is that when we do this sort of determination of the digits of the square root of 2, we examine each of the digits and we plug in the symbols 0 through 9, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, to find the pair that borders the property that we want. That is to say, 4 and 5 form this pair that border the property between having the property, that is squaring it producing 2, or in this case less than 2, and not producing something less than 2, that is exceeding 2. So hopefully you can see that when we do this sort of calculation using this notation, we're essentially creeping up upon having the exact property. We're creeping up upon the number such that when it's squared, will produce 2. And we're creeping up upon it because we're always adding something else. We're adding more and more positive numbers, but we're never actually getting there, which is essentially why we're never going to know the square root of 2 in general. We're never going to know all the digits. And one other thing I'd like to point out in this video is that if you haven't realized it yet in your mathematical education, you'll essentially observe it now, is that base 10 is arbitrary when we're trying to represent a number. We could have done this exact same calculation in binary, which is base 2, where we only have 2 symbols. We have the 0 symbol and the 1 symbol. So what I'd like to do is do this sort of computation of the square root of 2, or I guess in binary you would say the square root of 1, 0 in binary. Now the advantage here is that we only have to examine one symbol. We don't have to go through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We just check one symbol, namely the 1 symbol, to see whether it borders the property that we want. And just to introduce you to what a binary representation is going to look like, pi in binary looks like this. And as soon as you see this, don't read this as 11, because it's not 11. There is no 11 in binary. You should read it as 1.001001. We only have 2 symbols in binary, just ones and zeros, and there is no 11. But what this means is very much analogous to the way we set the notation in decimal. That is, this location here, which would be the ones place in decimal, or the 10 to the 0 place, is also the ones place in binary. But what it means is 2 to the 0, not 10 to the 0. So this is going to be the 2 to the 0 place. Now in decimal, this would be the tens place, but here it's going to be not the 10 to the first place, but the 2 to the first place. So it's really the 2's place. So from these 2 symbols alone, the 1 and the 1, this means we have one copy of 2, that is 2, plus one copy of 1, or 2 plus 1. So this symbol, these 2 symbols here, 1, 1, is the binary representation for 3 in decimal. And then after the decimal place, or I shouldn't say decimal anymore, I should say after this point here, the notation is very similar to decimal. This is the negative 1's place, or negative 1 power place. So this is the 2 to the negative 1 place, or the 1/2's place, followed by the 2 to the negative 2 place, or the 1/4's place. And then I keep going, the 2 to the negative 3, or the 1/8's place, the 1/16, the 1/32, and a 1/64 place. And this just means the same thing. So the 1 in that location means one copy of 2 to the negative 3, or 1/8. And then I go here, this is the 3, 4, 5, 6. So this means one copy of 2 to the negative 6. And so you add all that stuff together to get your number that you want to express. So just to put that out more explicitly, this representation means 2 to the first plus 2 to the 0, so we get 3 right there, plus one copy of 2 to the negative 3, or 1/8, and then we get one copy of 2 to the 6th, or 1/64. So the exact representation of this truncation of pi would be 201/64, which is equal to this in decimal. And you can immediately make an observation, is that you're only really getting 2 decimal places of accuracy here. 3 if you round it, but 2 digits of accuracy here. But it took you 6 digits here to represent it. So computationally, binary is very nice. There are only 2 symbols, but it takes more digits to get the accuracy you want. Let's now compute the square root of 2 in binary. And since we only have 2 choices, a 0 or a 1, in terms of what we're going to put into a column, we only have to check one symbol. So let's begin with the 1's place. So we observe that 1 squared, or 1 times 1, falls short of 2. Or in binary, you would just say it falls short of 1, 0, but we'll keep it as 2 for now. So that means that a 1 is going to go in the 1's place. So we know that the square root of 2 in binary is 1.0001. something, 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 where these digits are still to be determined. And now let's take care of the 1/2 place. So let's put the 1 there and we'll check it. So what is 1.1 times 1.1, where these are interpreted in binary? So this is going to be 3/2 squared, which is 9/4, which is greater than 2. Now since it's greater than 2, we're not going to put a 1 there. So that means we're going to put a 0 there. So we know so far the square root of 2 in binary is 1.0, and then something, something, something. So now let's take care of the 1/4 place. So again, we put a 1 there. 1.01 times 1.01, we perform that computation, which is 5/4 squared. And we get 25/16, which falls short of 2. So that means we're going to keep the 1 in that quarters place. So now we have, so far, 1.01. We then put a 1 in the 1/8 place. We perform the computation. We get 11/8 squared, which is 121/64. That falls short of 2. And so we keep the 1 there. And hopefully you can see the pattern so far. If it falls short of that property, we keep that 1 there. If not, then we replace it with a 0 and then move on. So far we have 1.011. Now we check the next place, put a 1 in the 1/16 column, perform the computation, and we get something which is greater than 2. So that means in the 1/16 place, I put a 0 there. And then I continue. I go on to the 1/32 place. I stick that 1 in there, and I get that falls short of 2. So I keep the 1 there. So to 5 digits after the point, I know that the square root of 2 is 1.01101. And the exact representation for that would be this thing right here, 45/32, which gives me this, which is it's a decent approximation for the square root of 2. But as we've seen before, we need more and more digits to get a certain level of accuracy. And if you want to look up what the more digits of the square root of 2 are, you just put that into Wolfram Alpha or Wikipedia or whatever. And here's some more digits here. And there are 13 places after the point there. And those 13 places will give you essentially 3 places of accuracy in decimal. So the reason I begin with those computations in base 10 and base 2 is just because it gets you thinking about what this notation means in terms of falling slightly short of a property or exceeding a property. So now let's relate all this stuff back to Dedekind cuts. And we'll examine our example, which is the square root of 2, which is all the rationals such that their square is less than 2 or they're less than 0. And to determine the digits of this, we're going to take a very similar strategy as we did for our other computations. We're going to look for the bordering digits, except now we're going to use the criterion of set membership. Before we were using the criterion of their square being either less than 2 or greater than 2. Now what we're going to do is check and see whether when we square them, we get something which is in the set or not in the set. So let's take care of the first digit. Let's try sticking a 1 in there. So we find that 1 squared, and now this is all rational number arithmetic, so this is completely fine. 1 squared is 1, and that number is going to be in the set, the square root of 2. And then we find that if we go one more place up, 2 squared is 4, and the rational number 4 is not in this set. So far, just like in our other computation, we know that the decimal expansion representation of the square root of 2 is going to be 1 point something something something, because we're looking for those bordering digits, and that's what's going to determine the decimal representation of the Dedekind cut. So far we have 1 point something something something. Now we move on to the next place, and we're kind of cheating here. Instead of examining all of the symbols 0 through 9, we're going to start right at 14, or I should say 4 right there, because we kind of know what the square root of 2 is approximately. So we check and see, just like we did before. The 4, when placed there, will produce something, will produce a rational number which is in this set. And then if you go one more digit up to the 5, it'll produce something not in this set. So now we have 1.4, then more digits to be determined. And then cheating a little bit more, since we know the next one's going to be 1, we find that 141 over 100 squared produces a rational number which is in the set. We go one more digit up to 142 over 100, square it. That produces something that is not in the set. So now we have 1.41 as a representation of the Dedekind cut. And then we continue on in this pattern until we get however many digits we want. So hopefully you can start to see how we can take these abstract definitions of Dedekind cuts as sets and, at least in our head, assign a decimal expansion to them and assign a unique decimal representation for them. Now, the only nuisance when you do this sort of procedure is the repeating nines. Now, to see that, let's take the Dedekind cut for 1, which is going to be all the rational numbers that are less than 1. So if you go through this procedure, go through all the symbols, you'll find that you're not going to get a 1 in that first place. Instead, you're going to get a 0, and then you're going to get 9s all the way after. So this is going to be the thing that the procedure that I just outlined will output. And if you, more generally, if you do this with any truncating predicate there, for example, x is less than 1/4 or x is less than 1/5, anything that truncates, or we kind of know that truncates, you're going to have the same problem. So 1/4 right there is not going to output 0.25 like you'd want it to. It's really going to output 0.2499999. And you should go through the computation to convince yourself of this. But one good thing about thinking about this is that when we go in the reverse direction, when we take a decimal expansion and assign it to a Dedekind cut, we're going to find that 1 and 0.999999 are going to get assigned to the same Dedekind cut, which means that even though for our practical purposes we might consider using this or taking this seriously, this infinite nines, theoretically they are representing the same object. So that would be a pretty big problem if this 0.9999 and 1 are representing two completely different objects. Now that's the question I'd like to discuss next, how you would assign, given a decimal expansion, how do you assign that to a Dedekind cut? Now for terminating decimals, I claim this is quite easy. If you're given 0.25, you can interpret that as 25 hundredths. And in part 16, I'm going to talk about embedding functions. So you can actually do this quite quickly there. And what you do is you just assign this to the set containing all rational numbers less than 25 hundredths. And you can show that that's equal to the reduced form, which is all the rational numbers being less than a quarter. So for terminating decimals, this is quite simple. Now for infinite decimals, we can essentially capture the whole thing in one fell swoop, just like we did here. We kind of went out to the end and said, okay, this 2.5 here means 25 hundredths. But I can't capture the whole thing, even with simple cases like 0.33333. So what we're going to do is work with truncations and build our way up to this infinite decimal. So we're going to work with this example, the 0.3333 repeating. Now each of its truncations, 0.3, 0.33, 0.333, 0.3333, are by themselves quite easy to represent. So what we're going to do is we're going to let the infinite decimal, 0.3 repeating, be represented as an infinite union. And we're going to have it be the infinite union of each of these truncations. So this infinite decimal, 0.3 repeating, is going to be the cut corresponding to 3/10, unioned with the cut corresponding to 33 hundredths, which is that one right there, unioned with the cut corresponding to 0.333 or 333 thousandths, union with the cut 0.3333, which is down here, and so on. We're going to keep unioning all of these truncations, and that's going to build its way up to the infinite decimal. So what we're claiming is that this infinite union is identical to the cut corresponding to the rational number 1/3. And to do that, you would prove that just like any other equality between sets. You would show that all members of this infinite union are members of this set. That is, this is a subset of this set, and this set is a subset of the infinite union. Now, if you notice here, in the process of this infinite union, the next higher level set, that is, let's take this set for example, this set is a proper subset of this one. So when I decide to union on this one, this is equal to the larger set. This is the larger set here. And then I union on some other set, and it's now equal to that set that I've built up so far. So I'm building up unions of proper subsets upon proper subsets. So it shouldn't be too difficult to convince yourself that this infinite union is a subset of this one, because you're building your way up to that set. Slightly more difficult is to show that this is a subset of this infinite union. That is, any member of this cut is found somewhere in this union. And if you're computationally oriented, you can actually determine which one of these cuts will contain some test value. For example, if I give you a rational number which is just slightly short of 1/3, that is, it's in this set, it's just slightly short of 1/3, you can tell me in which one of these truncations that rational number will begin to appear. And you can actually prove that by thinking of geometric series. That is, these represent partial sums in a geometric series, and there's a nice formula for that. And so you can actually compute which one of these sets a test value will start to appear. So I encourage you to play around with that idea of building up these truncations to get to the infinite decimal. And as I claimed before, this procedure of assigning a decimal representation to a Dedekind cut will actually assign 0.9 repeating and 1 to the same Dedekind cut. So essentially what we're claiming here is that if you take this infinite union, which is going to be these sets here, made up of the 9/10ths cut, union with the 99/100ths cut, union with the 999 1,000ths cut, and so on, is going to be the same as the cut corresponding to 1. So that would verify that these two representations are being sent to the same real number. So essentially you'd have to show this equality to show that these two representations are being sent to the same real number. And as before, with the case of 1/3, I encourage you to actually verify that. And that'll wrap up this video. Just as a disclaimer, a lot of the stuff that I presented in this video isn't coming from a standard textbook, like an analysis textbook or a set theory textbook, just because you can't find a lot of this stuff in those textbooks. They just don't give a damn about doing computations or anything like that. And if you find any details that I haven't covered or any ambiguities, there's a reason for that. This is stuff you can't normally find in a textbook that's geared toward pure mathematics. So if you find anything interesting, feel free to add to the discussion. Leave a comment or make a video yourself, explore this topic on your own, and stay tuned for more videos. Thank you.